Gravimetric stoichiometry. Stoichiometry is a method of predicting the quantity of a reactant or a product in a chemical reaction based on the quantity of another reactant or product in the same reaction. Gravimetric stoichiometry is some sort of stoichiometry that involves the mass of substance. Okay, so a mass is given when we're looking at gravimetric stoich. To solve a stoichiometry problem, there's 5 steps that we're going to do over and over and over again. We need to write out a balanced equation, write out what we know from the question below each compound. We're going to calculate the number of moles of a known chemical. I'll define that in our first example. We're going to convert the number of moles of known into the moles of unknown, maybe. We could call that using our mole ratio. And last but not least, we're going to basically solve the question, convert the moles of that unknown into whatever we're looking for. Note that we're going to use 3 different steps of calculations. So we're going to get 3 answers here. We are not going to round to our appropriate number of significant digits until the end. So we're going to keep it at least the number of significant digits plus 1 extra in all steps. Now, this doesn't mean that you have to retype that exact number into your calculator. Use your unrounded value in your calculator. You just don't have to write the whole thing out on your piece of paper every time, if that makes sense. I'll show you what I mean in the next example. When the oxygen in air reacts with iron, rust, which is iron 3 oxide, is formed. What mass of oxygen is used for every 100 grams of rust formed? Our first step, remember, is a balanced equation. Second step is to write out info. The first calculation, or third step overall, is calculate moles of the known. We're going to switch moles. And solve. All right, so our first step, we need a balanced equation. It wasn't given in this equation, or this question, sorry. Oxygen in air reacts with iron to form iron 3 oxide. Remember, iron 3 means Fe3 plus is combining with O2 minus. When I write an ionic compound, I need to balance for charges before I can even write this in the equation. So I need 2 irons and 3 oxygens to balance the positive 3 and negative 2 charge. Rust is also a solid. All right, this is an equation, but it's not yet balanced. So let's balance this one. There are 2 irons here and only 1 on this side. So I would look to putting a 2 here. However, now there's 2 oxygens and 3 oxygens. So the 2 isn't good enough. I'm going to need to up the ante here. So let's double this. That gives me an even number of oxygens to work with. Okay, I now have 6 oxygens in my products and only 2 in my reactants. So I'm going to write a 3 here. That now gave me 4 irons in my products. So I'm going to put a 4 here for our iron. Okay, we are looking for the mass. That is the end of step 1. We've balanced our equation. Step 2 is to write out the information that was given in the question. What mass of oxygen is used for every 100 grams of rust formed? So if we produce a mass of 100 grams of rust, we are looking to solve for the mass of oxygen. So we've written out all our information. All right, our first calculation step is to calculate the moles of known. The known in every stoichiometry question is the one with information below it, the one that doesn't have a question mark. So Fe2O3 has information below it, unlike iron, has no information. Has information below it, no question mark, it is my known. Because technically, I can calculate moles from this information given. I know the number of moles. I just have to work to get them. The unknown in this question, and in any question, is the one with a question mark. It's the one that I have to work hard to find the moles of, or use stoichiometry to solve for. Okay, so let's calculate the number of moles of known. I've been given mass. To find moles from mass, I need to use the formula. So this is step 3. N is equal to little m over big M. I have mass. I just need to calculate the molar mass of Fe2O3 before I can continue. Note, a lot of us, when we look at this, are concerned that there's a 2. When I calculate the molar mass of something, I never include the coefficient. This could be 2002 moles of iron oxide formed, and the molar mass will still be the same as 2 moles. Okay, the molar mass is 159.70 grams per mole. All right, so let's put that into our equation. We're going to calculate the moles of our known. So 100 grams divided by 159.70, and we get 0.62617 moles, and that is of iron 3 oxide. Okay, so we have now calculated the number of moles that 100 grams of iron 3 oxide represents. So we are done step 3. Now, to be able to talk about information about oxygen, to go from one compound to another in an equation, we need to use our mole ratio. So this is how we're going to switch moles. We're going to go from moles of iron 3 oxide, which we just calculated, to moles of oxygen. Again, this is using our mole ratio. This is step 4. So we're going to take our just calculated value, and I'm going to multiply by a fraction. In this fraction, I always want to cancel what I've started with. So moles of Fe2O3 need to go on the bottom to cancel. Because I'm interested in switching moles from iron to oxygen here, iron 3 oxide to oxygen, I'm looking for the moles of oxygen. So they need to appear in the top of my fraction. Now, to fill this in, every time we go to fill this in, we are looking at the coefficients of the balanced equation. So I know that it took 3 moles of oxygen to make 2 moles of iron 3 oxide. Notice that I put the coefficient where I put the compound, okay, in the mole ratio. All right, moles of iron 3 oxide cancel, and I am left with 0.93926 moles of oxygen. That's the unit I have left. So we've done step 4. We have switched moles from one compound to another. Our very last step is to solve the question. So technically now I have this number of moles. I could write this underneath oxygen if I wanted. So our 5th step is to solve for mass. I'm going to use this exact same formula, just rearranged to solve for mass this time because I have moles and I can very easily get the molar mass. So moles are what we just calculated, 93926. And the molar mass of oxygen, remember it's O2, is 32 grams per mole. So multiplying those out, I get 30.056, and I'm going to round that 3 to a 4 here. This is grams. Our very, very last step is to consider significant digits. The only piece of information, measured quantity from our equation, or our question, has 3 significant figures. Therefore, our final answer should also have 3 significant digits. So 1, 2, 3. However, this 5 makes me round this up. So I'm going to write this as 30.1 grams. Notice I needed 3 significant digits in my final answer. For each of my steps in my calculations, I kept at least 3 significant digits plus 1. So 1, 2, 3, and then extra 1. I had to at least write this 1, which would have been rounded up to a 2. Okay, so keep at least 3 significant figures in your interim answer. This is not our final answer. Plus 1, so we're going to keep 4 the whole time. I just used my unrounded values every time in my calculator. Like I took whatever this was, it had more decimals, and multiplied by 32. So mine represents a more accurate. However, if you just typed this into your calculator and then this into your calculator to multiply by 32, you would still get a very, very close answer. It's when we start rounding too soon that we might get a rounding error. Maybe you would get a 3 here instead of a 1, and you would get this question incorrect in our assignments. Okay, so just make sure you keep at least 3 plus 1 significant digits in this question. Another example here. A teacher mixed 47.3 grams of solid sodium phosphate into solution. Students added excess calcium nitrate solution to this mixture, meaning that we have more than enough calcium nitrate to react with all of our sodium phosphate. What is the name of the solid formed, and what mass would the students expect to find after filtering the solid? So what they're saying is that this reaction makes a precipitate. Let's write out our balanced chemical equation, because that is step 1. Okay, sodium phosphate is Na3PO4, because PO4 has a 3- charge. And they've told us that they've mixed it into solution, so it's aqueous before we react. We then add calcium nitrate, which is also aqueous. It's a solution. This is a double replacement reaction where calcium is going to combine with phosphate. Now remember, calcium is a 2+, phosphate's a 3-. So to write a neutral charge for this ionic compound, I need to include these subscripts. And then sodium is going to combine with nitrate. To find out who's the solid, I'm going to use the solubility table on the back of our periodic table. You'll find that this is insoluble and this is soluble. This is just an equation. It's not yet balanced. So I'm going to start with calciums. There are 3 calciums in my products and only 1 in my reactants currently. So I'm going to add a 3 here. Now, calciums are balanced, but I now have, 2 times 3 nitrates. So I have 6 nitrates in my reactants. I only have 1 nitrate in my products. So I need a 6 here. This now gives me 6 sodiums in my products, and I only have 3 here. So I'm going to add a 2. This gives me 6 sodiums and 6 sodiums were balanced, and 2 phosphates, which we already have in our products. So we have balanced our equation. Step 2 is to write out our information. So we mixed a mass of 47.3 grams of sodium phosphate into solution. There's no numbers given for calcium nitrate, so I don't need to write anything for that. So what is the name of the solid formed? Well, the name is calcium phosphate. And what mass would the students expect to find after filtering the solid? So they are filtering this precipitate. We're looking for the mass of this guy. All right, so we've written out our information. Our third step is to calculate moles of our known. In this case, our known is sodium phosphate because I have information about it. My unknown is the one with the question mark every time, and that is calcium phosphate. To calculate moles of my known, I'm going to use the same formula as we did last time. N is equal to little m over big M. So 47.3 grams divided by, we need to calculate sodium phosphate's molar mass. If you pause now and do that, we'll compare answers. I got a molar mass of 163.94 grams per mole. So let's put that in here. And we're going to divide our 47.3 by that number. I get 0.2885 moles, and that is of Na3PO4. Notice that I always put this little subscript once we're talking about moles, because we're going to end up talking about moles of two compounds, this one and this one. I've also taken into consideration my significant digits just for my calculations here. In the end, I have 3 significant figures. So I need to keep, through my calculations, 3 plus 1, I need 4 significant digits, at least. 1, 2, 3, 4. I can add more, I just can't keep less. All right, we've calculated the moles of known. From there, we need to switch moles. That is really hard to read, sorry. So we need to go from moles of sodium phosphate to moles of our unknown calcium phosphate. This is using our mole ratio. So we're going to take the number we just calculated, 2885 moles of sodium phosphate, and we are going to multiply by our mole ratio. Moles of sodium phosphate need to go on the bottom because that's what we're trying to cancel. Moles of calcium phosphate go up top because that's what we're trying to find. Remember, the numbers that fill this fraction are always the coefficients from our balanced chemical equation. That's why we needed it. We need our equation for step 4. All right, if there's no number in front of something in our equation, we assume that that means a 1. And then there are 2 moles of sodium phosphate. So we're going to divide our number by 2, and we get 0.1443, if we're rounding here, moles of calcium phosphate, because moles of sodium phosphate cancel here. Our very last step is to solve the question. We are looking for mass, and we just calculated moles of this. So, using moles to find mass, I'm going to use just a rearrangement of this formula again. Mass is equal to moles times molar mass. Let's pause and take a moment to calculate the molar mass of calcium phosphate. I think it's really important that you take a moment to actually calculate this just to make sure that you're doing it properly. I got a molar mass of 310.18 grams per mole. So we're going to take our moles that we just calculated, 443, and we're going to multiply by that answer. Remember, I'm using my unrounded value in my calculator, so the one that has more decimals on, and I'm going to multiply that by my 310.18, and I get 44.746596. Lots of decimals, more than I need for sure. Remember, in the end, we want to keep 3 significant figures for our final answer. So I should round this to 44.7 grams. Now, there's one other way to do stoichiometry. We're going to take the exact same first 2 steps. So we're going to write out our balanced equation. I'm just going to copy it from above. So 2Na3PO4, 3CaNO3, 2 makes CaPO4, 2, and 6 NaNO3s. Writing out what we know, 47.3 grams, mass is a question mark. Notice that anytime we have a mass listed in our information, we're going to need that molar mass. So I'm going to go ahead and just copy these down as well. Okay, so you could always just calculate these out right away if you see a mass in the information for that compound. All right, this is called unit analysis. The way that this works is we're going to start with our only piece of information, our known information, 47.3 grams. I need to cancel grams, and my first step was always to find moles, and that would have been of Na3PO4 in this case. Notice that moles per gram doesn't really mean anything, but grams per mole sounds familiar. This is because for sodium phosphate, 163.94 grams is equal to 1 mole of sodium phosphate. So I'm going to put that information in to this fraction. There are 163.94 grams per 1 mole of sodium phosphate. Notice that grams cancel. That was the whole idea. So at this point, if I pressed enter in my calculator, I will have calculated the moles of sodium phosphate. That was our first step. Once we have moles of sodium phosphate, we need to cancel moles of sodium phosphate. And we are looking to find moles of calcium phosphate. So we put in our coefficients again. There is 1 mole of calcium phosphate per 2 moles of sodium phosphate. Notice that moles of sodium phosphate cancel. The only unit I'm left with here would be our moles of calcium phosphate. Calcium phosphate, sorry. And that was our second step. So what we're doing is we're using units to go through our steps rather than formulas. All right, our very last step. We need to convert moles of calcium phosphate into grams because we're looking for mass. Now, again, the units of grams and moles together could only mean our molar mass. For calcium phosphate, 310.18 grams is equal to 1 mole of calcium phosphate. So putting this information in, 310.18 with the grams, so 310.18 grams per 1 mole of calcium phosphate. Last step here, our moles of calcium phosphate have canceled. The only piece of information I have is grams, specifically of calcium phosphate. To solve our unit analysis, we are going to multiply all the way across the top and divide. So we're going to multiply all of these numbers together, and we're going to divide by all of the numbers multiplied across the bottom. In the end, we're going to get the exact same answer, and we're going to round it to 44.7 grams. It doesn't matter which method you use. To get comfortable with stoichiometry, I would say start with formulas. If you're like, man, this made so much sense, this unit analysis, go for it. But if you're confused as to why I chose each of these units, go back to formulas. Get comfortable with using formulas and working through these 5 steps every time, and this can come. We've got lots of time.